Hey everyone, and welcome to episode 2 of the Gearx Mark I Systems Introduction series, where we'll be diving into two systems, the Mark III Stator and the Mark VI Rotor. For those of you who are joining us for the first time, welcome. Gearx is an open design for a portable, printable magnetic generator. If you'd like to join our core developer team, feel free to check out our gearx.org website and jump over to patreon.com/gearx to check out all the benefits for patrons, including access to our developer Discord server. Now with that out of the way, Lucy, punch the title. Lucy? Lucy couldn't be with us today because she's on a pony farm having the time of her life. So I guess I'll have to do this myself. Yeah. So let's begin with a bit of role differentiation between stators and rotors. If you're already familiar with what these are, feel free to skip ahead about 30 seconds. For those of you who are not, stick around and I'll get you up to speed. Stators get their name from the word stationary, and rotors, you guessed it, from rotation. Stators typically function as a housing or scaffold to which magnets or induction coils are attached. Energy essentially flows through a stator, either to or from the rotating component of a system, aka the rotor. Rotors, on the other hand, have a shaft in the center to facilitate rotation, with a cylindrical array of permanent magnets or induction coils based around the shaft. Without going into the physics of electrical current, you can deduce that rotors can either be used A, to create current, for example in the turning of a generator, or output torque energy, in the case of an electric motor. Here are both examples side by side where a simple induction coil represents the rotor and the large magnet, the stator. There are minor differences between the two designs, but they're essentially the same systems in reverse. Now let's get cracking and take a closer look at the features of the Mark III Stator. This iteration has three printable parts, which are the induction coil scaffold and a pair of infills for the USB connectors. On the base, there are a pair of symmetrical lips which keep the scaffold locked into the chassis. It's worth noting that all Gearx Mark I designs are symmetrical to keep it as balanced as possible. Inside the recesses for the USBs are pairs of ports for the wiring which connect to the induction coils. There are 12 rectangular angular extrusions for mounting the induction coils. On this example, I've installed test coils which collectively can produce 0.2 volts AC between both stator hemispheres. I also want to say that these test coils were primarily for testing the system continuity, and since I've never made induction coils by hand before, I just had to try it out. Also, just as a heads up, there are some minor compatibility issues between the current stator and rotor, which we'll get to in just a second. For those of you who may be wondering how each of these systems are made and want to know more, I'll be making a step-by-step video guide on how to build them once I'm finished with filming this introduction series. So let's keep moving. Here you can see the coil terminals collecting at the top and bottom, where they are then soldered onto some speaker wire, which is then soldered onto the USB terminals. Lastly, and at the center of the stator, you'll notice a powerful 25 by 20 millimeter cylindrical neodymium magnet. This bad boy is essentially one half of the frictionless coupling for our shaftless rotor, and is where some of the compatibility issues I mentioned start to surface. Let me show you with one half of the rotor assembly. You'll notice that without pressure applied, this rotor hemisphere spins freely and is a happy chappy. But when both halves are joined to the chassis, either the pressure on the assembly is too high, or there could be flux field interference from neighboring magnets causing the rotor to decentralize. Another important feature of this system is the flux plane it creates inside the rotor with these strong magnets facing each other, which keeps the rotor afloat. I like to think of it like pressing two tennis balls together. The contact areas flatten out, which equates to flux field manipulation in our case, and it's just one of the ways you can shape magnetic flux fields. Just so you know, the system is very time consuming and has had some of the most work done on it, so please feel free to help me out with it. Now let's have a closer look at the rotor, starting with the other half of the frictionless coupling. The rotor is made out of three parts: the rotor hub, the boss, and the drive ring. We won't be covering the drive ring today because it is actually primarily part of another system. The boss is essentially the other half of the frictionless coupling. It has three locking teeth around its perimeter, which is currently being reviewed and improved, and 2 magnetic arrays that form the coupling. One array sets the ride height of the rotor using 5 by 3 mm stacked cylinder magnets, and is also a cushion for the rotor against vibration and shock forces. The second array uses custom monopole arc magnets which centralize the rotor around this large coupling magnet. Pretty cool, but could be better. We'll get there. Now let's move on to the rotor hub. The open side has a lip which fits into the drive ring on both sides. I'll quickly show you now. On the exterior of the hub, you'll notice the induction magnet array. These all have the same pole facing in the same direction, and you'll notice they are sequentially offset. It is not yet clear if this is enough of an offset to create the best possible induction pulse into the stator with the amount of room that we have available, but we'll find out shortly. If you want to learn more about induction, look up Faraday's laws of electromagnetic induction. You could think of this like trying to brush your hair or beard with either something purely cylindrical versus a comb or brush. The variability does the work. There needs to be a level of variability in flux field strength in order to induce a current into the coils, and the space needs to be used efficiently too. Also, don't forget to bear in mind that the Mark I is all about using components that are available anywhere off the shelf, bar a few custom-made parts. Efficiency is a high priority, but not at this current stage of development. To finish up, I'd like to touch on where these systems are at, the changes that are needed, and what to expect in future iterations. This current stator iteration is a bit too snug on the lower part of the rotor. This may mean that we need 2 different stator sizes to fit the top and bottom of the rotor. Once this is done, then the induction system can be tested completely, along with the drive system. Speaking of, the rotor hubs and the drive ring need updating so that symmetrical orientation of the hubs can be ensured every time. Right now you can connect the hubs any way you want, and that will affect the center of gravity and stability of the rotor. We will need to convert this lip into a sectioned lip with corresponding grooves in the drive ring. The coupling system also needs revision and will probably get updated together with the hub. If anyone wants to jump in and make suggestions for improvements, please do. So, that about wraps up our second Gearx Systems Introduction video. In the next episode, we'll be covering the drive ring and control jaw, with a sneak peek of some drive system testing. I don't want to get you guys' hopes up, but I want to say this system is the most tested and least developed of all Gearx Mark I systems. But I guarantee that you'll learn something. If you have any questions or comments, leave them in the comment section below. Thank you for watching, and I'll catch you in the next one.